morning. I will begin my talk with a very short story of variational principles in physics. So first of all was Snell's law. Of refraction, but this is just a problem of a quickest or shortest time, yeah? So imagine that we have a horseman here, and he must go there, and here there is a grass, which means that the horse may walk relatively fast with velocity v1, whereas here we have a sand, velocity is much slower. So the first conjecture would be to choose the straight line, but it is obvious that it is not optimal. Why? Because it pays to slightly shorten the to slightly shorten the trajectory where the horse goes slowly, even if this trajectory will be longer. So finally, there is some balance which must be fast. Of course, this problem is just a trivial problem in calculus. Namely, everything depends upon the choice of the transition point, which means that the time is simply the L1 divided by V1. So this is a time which is necessary to make the first part of the trip, plus L2 divided by V2. And this is a function of this point, which let me call x. So this is just a function of a single variable, and our students are well prepared to calculate the minimum of that function. And as a result, we obtain the Snell law, namely, if I call this angle θ1 and the other θ2, so the Snell law tells you that sine of θ1 divided by sine of θ2 is equal V1 by V2, and that's all. 1661. Now, next step is a Fermat principle, namely the trajectory of a light rain in a, so now is Fermat. So the geometrical optics in a non-homogeneous medium, which means that there is a medium whose velocity depends upon its position. X, maybe I will say X, just a position, even if it is, whether it is two-dimensional or three-dimensional, it doesn't matter. So the Fermat approach was the following. Let us suppose we observe such a trajectory of a light ray. Let us approximate this curved trajectory by a polygonal chain, yeah, or polyline, which simply means that we divide this medium into pieces such that the velocity is constant over there. And in that case, of course, there is a Snell law on each transition point, which means that this time depends not upon a single variable, but upon many variables. Yeah, so t, x, say 1, x2, and x.
Jurek, I have a question.
Yeah.
Just Christian. Yes. So, I mean, you said there is a Snell law, but of course, because we take it for granted, but actually, where does it come from? It's not obvious that there should be a Snell law here for light. We've been taught that there is a principle like that.
Question.
Where it comes from, the Snell's law?
The
For
Snell's
light.
law comes from look.
But this is for a horse. But why should light
physically,
know that
it was
wants
just
to go fast?
assumed by the Snell, because people have observed already that there is some relation between sine and sine. Physically, they have measured, and there have been conjectures that, of course, at that time, nobody knew what is the velocity of line. So, but people were not happy with just experimental measures, but were looking for physical laws. So Snell conjectured that the velocity is different and has derived mathematically this Snell law, and it was in a very good agreement with, and that's all.
But I mean, this should be derivable from Maxwell equations, right? So that's this is a postulate for you, right? So you're saying, well, we assume geometric optics minimize this time of arrival period, but this should be something which should be derived from Maxwell equations, should it not?
Well, of course, it can be derived from the Hohenheim's principle.
Yeah, of course. Yeah, later on, when people have understood the wave nature of the, and so on and so on. Remember that at that moment, it was just a conjecture. Yeah. In 19th century, for instance, nobody has seen any atom. However, there was a huge part of physics and chemistry based on this conjecture that there are atoms, particles, and so on and so on. Yeah, so this was just a physical conjecture. But I am talking here about mathematics, and most of scientists has agreed, has taken this as a proof that his conjecture was, and Fermat pushed it forward, namely, now X is just a X1, X2, and so on, X3. And this is nothing but a sum, the same sum as here, yeah? Something like L E over V E, and because we know that the Snell law at each transition point means that when we fix all the axes except just one, then the line is shortest one. And now, if we make this division finer and finer, we finally obtain such a integral. And this is a heuristical proof that in a continuous case, we should minimize this quantity. And the interesting thing is that this is just 1 over V, which is position depending, and the square root of GKL, this is position depending, yeah, dx k dxl, which simply means that if we define such a fictitious metric tensor, which is 1 over VGKL, which is, sorry, square, V squared, because I must put it, which simply means that the light rays travel over shortest lines or geodesic line of this fictitious metric. Okay.
That's like 1621.
So,
1621, not 61. Snell's law. Much
yes, sorry, of course, excuse me. The next step was brachistochrone problem. 16, this I know by heart, 96, Johannes Bernoulli. I write his name because they have been 4 brothers Bernoulli, and this is that one who invented this problem. He invented this just as a puzzle, which he sent to leading mathematicians of his time as a challenge. Are you able to solve this problem? These people, among others, because there are probably many more, but I remember 3 of them: Newton, Leibniz, and de l'Hopital. Yeah, and all of them have solved this this problem, which I'm going to cite, namely, if you take such a profile and you put a ball here, then we are able to calculate the time of arrival here. We put the ball with initial velocity 0. Is there any profile such that the ball arrives faster? And especially, which profile is the best one from this point of view? Again, to find the shortest way. Yeah. And of course, like over there, we immediately see that it pays to first to put the ball very almost vertically, because this way the ball will get quickly the velocity, and then even if this path is slightly longer, but velocity is much bigger, therefore it pays off. But of course, we cannot exaggerate, so there is some balance which must be done. Okay, so this brachistochrone, the shortest time curve, at that time, people have used names taken from Greek or Latin, so brachistochrone. So this optimal line, and this is, by the way, very nice exercise for first year or second year calculus students. Those of you who teach them calculus, I think it is very nice to consider this problem. Now, but the main personality which appears in my history is Maupertuis, Pierre-Louis de Maupertuis. Those of you who have studied, yeah, okay, all of you have studied classical mechanics, so you know probably Maupertuis variational principle. It is a principle for trajectory and so on. Maupertuis was very much influenced by the optimistic Leibniz philosophy, which was related with the fundamental problem in philosophy. The fundamental problem, it is known in philosophical literature as unde malum, where the evil comes from. Because if the God has created the universe and the God is good, where there is so much evil? And the answer was, roughly speaking, like that, that some aspects probably are not so good, the others are good, but there is a balance, and the God has chosen the optimal word. Here, for instance, if you shorten the line, which you improve some aspect, but the other aspect, namely velocity, will be worse. So the same choice had a God when creating the universe. He had chosen the best of the world, the best of possible worlds. And for that purpose, he has invented this name, least action. No, action is probably later, but something was least. Something was least. And the God in his, has chosen the word when creating it in such a way that functional assumes its least value. Later on, there have been slightly later, because this was around 1750, roughly speaking. Immediately then, people got interested in these problems, and Euler and Lagrange a bit later. And we are taught that the variational principle is equivalent to Euler-Lagrange equations. Everybody knows it. So, no, sorry. I have to. Okay. Okay, so let me derive Euler-Lagrange equation, which is a stupid thing because all of you have done it many times during your studies, but let me just derive it in order to point out some important things. So we assume that we have of course, the next step is Hamilton. Sorry, excuse me. Hamilton, because I will mainly discuss Hamilton variational principle, which is a generalization of Maupertuis. However, Maupertuis' invention was fundamental. Just Hamilton has slightly broadened. Okay, so let us come back to our century. So most of physics, of theoretical physics, is based on the Hamilton variational principle, which means that we have a Lagrangian density, which depends upon some fields and their derivatives. Okay, this is just abbreviation for the partial derivatives of K. Here, I use partial derivatives, not any covariant derivatives. At my time, when I was studying physics, not in this building, but in the other one, then using partial derivatives was something embarrassing, yeah? Yeah, embarrassing. Somebody who has used partial derivative was treated, he doesn't understand that real geometry is just is based on covariant derivatives, and using only the peasants use partial derivatives. But here, no. And partial derivatives are legitimate operators. This is based only few times later, a few years later, I noticed that there is a nice geometrical object which is described by partial derivatives, namely jets of sections and so on and so on. I am not entering into that because for our purposes we may remain on a very basic level. Of course, those quantities in physics very often are organized into some some bundle, geometric bundle. So these are values of our fields. And in mathematical language, they are coordinates in each fiber of this bundle. And these are coordinates in the altogether, this is the first jet of a section of that bundle. Now, I will remain on the level of first order derivatives. However, it may include also derivatives up to 10, or if you prefer 20, let it be 20. Everything goes in a similar way. However, there are some subtleties which have to be taken into account, but today I'm going to stay on the level of first order principle. Okay, so what we do? We consider a one parameter family of course, the physical field depends upon position, yeah? But it depends also upon a parameter, and we'll calculate derivative with respect to that parameter. I call it delta. So this is nothing by d over d, say, epsilon. Therefore, you have to understand that all those quantities depend upon position, physical position, which mathematically is a base of this fiber bundle. So x, mu, and epsilon. Okay. Okay. And now,
you include time into x mu.
pardon?
You include time into x mu. Time.
Not only time, everything, time, position, and so on. This is a point of space-time. When it is, however, it may be just a chemical technology. Then it is mainly when we are interested in equilibrium processes, then there are only positions, and so on and so on. It may also be one-dimensional. Then this is just a classical mechanics. And let me calculate the derivatives of this quantity at a single point. So what is it? So it is dl over d phi k times derivative of phi with respect to epsilon, which is simply phi k, and also the there is also epsilon here, therefore plus dl over d derivatives times delta phi k mu. But this, you remember, is a this is a derivative with respect to space-time parameters. But the second derivatives are symmetric. Therefore, I may write down that this is d mu delta phi k. Yeah. Sometimes this commutation in old books is called fundamental principle of calculus of variation, but here you see it is nothing especially exciting. Just second derivatives are symmetric. Therefore, we may integrate by part. Yeah, we may integrate by part. So finally, we obtain dl over d phi k minus the d mu dl over d phi k mu, and this is multiplied by delta phi k, and moreover we have this total divergence, which I will write this way: d mu dl over d phi k mu delta phi. Okay. Now, the philosophy of all these people was the following: that this formula we use when we by integrating. Yeah, so we divide the action. If this talk had been given 100 years ago, I would probably be forced to use the letter V, because at that time physics was almost entirely German science, so action was called Wirkung. But nowadays, but in many books, action is still called W. Okay, but no, this is action, which is related with some space-time volume, which is defined as an integral over O of L. Now, most of you would protest, because would say, no, you must, if you integrate, you must choose, so something like D for X should be there. No, because this has already integrated into L. L is not a scalar function which you integrate, but it is a density. Of course, if you choose a system of coordinates, you may always write it as a product of a certain scalar times D for X, but from the very beginning, I assumed that L is not a scalar, but a scalar density. Therefore, the integral does not depend upon the choice of coordinates. Okay. And the philosophy is the following, that we are looking for minimum or stationary point with a condition that the boundary has been fixed. Yeah, so if we calculate, so delta A delta is equal integral over O of this Euler-Lagrange. These are Euler-Lagrange equations, so I will multiply by delta phi k plus an integral of the total divergence four-dimensional. Four-dimensional, if we think about field theory, therefore, it will be, we may change it to a boundary integral due to Stokes theorem. And let me just introduce this notation, which is very often, sorry, I am not, which I will use because it really pays to use this philosophy, namely this quantity, let me call P. And what is this quantity? First of all, position of indices. Of course, something which is up in the denominator, it means that in fact it is down. Yeah, therefore P has an index here and mu is up. Yeah, so this object is nothing but d mu p k mu delta phi k. At the moment, it is just a notation, but it is very important. One of the, yeah, so this will be p k, and I will write this way, orthogonal with respect to the boundary. Yeah? Times delta phi k. And now the story goes like that. There is neither minimum nor stationary point altogether. However, if we fix the boundary, the boundary values, which means that phi k at the boundary is fixed, which means that we move ourselves within the, a subspace of those field configurations which fulfill this boundary, then the delta of P within this family vanishes. Yeah. So if we fix boundary condition, then, and this way, this integral drops out, and now to find a stationary point or the minimum is just to find where it is zero. Now, this must be zero for any delta phi fulfilling boundary conditions, but doesn't matter. It immediately implies that this must be equal zero, and we are happy. We have now already in 30s physicists, but I'm sure that intelligent physicists had realized this much earlier, that of course in dynamical theories there is no minimum, that the Maupertuis terminology, least action, is absolutely false, because it is not a stationary minimal point, but a stationary point. By the way, a lot of mathematical effort has been done also in last century. For instance, there is a book, beautiful book by Gelfand and who? Oh, Fomin. Gelfand and Fomin on variational calculus, and their effort goes towards the sufficient condition, because this equals zero is a necessary condition for a minimum. But of course, people who are working in economy or in all of them who try to optimize something. Then they are not happy with fulfilling only necessary conditions. They would like to know whether it is really a minimum. And a very nice mathematical effort was done in this direction. But for us, it is irrelevant, because for us who are interested, I mean, for those of us who are interested in dynamical theories, we know that there is never minimum. Just take, for instance, harmonic oscillator. And it is just an interesting, very simple example to prove that this stationary point is not a minimum, but it is a saddle point. It is just stationary point because there are deformations of a trajectory which improve, this way, and there are different which for which the action is bigger. Okay, in any case, when this, so instead of a least action principle, we in fact have stationary action principle, and this stationary action principle was a basis for Feynman integrals. This stationary action which gives most contribution to the quantum, and so on and so on. You know, it's stationary action. Okay.
Saddle point method.
Yeah. Saddle point method. Yeah. This is very important. Also, WKB is based on that. And so, yeah. In any case, this is, Therefore, people have a tendency to say, I calculate the variation of the Lagrangian, I split it into two parts. This part drops out, it is irrelevant. So the only thing which we have is this part. This part is volume part and the boundary part. So people have a tendency to kill the boundary part and to concentrate on the volume part. Okay, so let us see how does it work. For instance, I will show you that it is a nonsense. Such an approach in hyperbolical theories is a nonsense. Although, of course, it is a, no, sorry. Sorry, I am not sufficiently intelligent or sufficiently trained, or however, 2 years ago I had I kept a lecture for students of the third years, and at that time I was very well trained in this machinery, but I forgot my training. Okay, so let us apply this for a simple hyperbolical. However, I stress that this is a perfect and legitimate approach in logistic, or if people try to construct for the traffic engineers, if they try to construct in Warsaw the green waves, green waves, they have to minimize something, and they solve this problem. And all this technique is perfect. Namely, the boundary term is irrelevant. The only part which counts is the volume part. Now, let me take the wave equation, and even in 2 dimensions. My personal almost 60-year experience is that if you are trying to say something about, for instance, I don't know, gravitational waves or something, check how your technique works in the case of wave equation. Wave equation is a mother of any hyperbolic equations. All the phenomena can be checked. So let us check how does it work for a wave equation. In wave equation, Lagrangian is equal -1/2 g mu nu d mu phi d nu phi. There is 1 because I prefer to use minus plus convention. Of course, those of you who are mainly working with spinors probably prefer the opposite, but I am mainly working with gravitational energy, and considering space like geometry with 3 minuses is very unpleasant. So I prefer this, which simply means that now x to simplify my example, let us choose just 2-dimensional Minkowski space, namely T, which is x0 and x. That's it, yeah, 2-dimensional. So this is nothing but 1, 2, and there is phi dot square minus phi prime square, whereby dot so phi dot is d over dt phi, and phi prime is d over dx phi. Okay. So you perfectly know that Euler-Lagrange equations is just a 2-dimensional wave equation, very often called string equation, which is nothing but, well, let me check which convention I used. Yeah, okay. d2 over dx square minus d2 over dt square phi equal 0. And you know how to solve. Every solution is a superposition of right-going and left-going signals, and you know it. But this equation may be nicely rewritten in terms of the light coordinates, so much beloved by Jurek, for instance, and indeed it helps very much in many circumstances. So let us choose coordinates u equal x plus t, v equal x minus t, and now d over dt can be expressed in terms of those, yeah? It is some combination of d over du plus d over dv. And what are the coefficients? Of course, du over dt, and the coefficient here is dv over dt, and du over dt is 1, and this is also and this is minus. So it is nothing but d over du minus d over dv. I use my notes because sometimes it is difficult not to make some error in the sign. So, okay, and the same for d over dx. Recently, I had been asked to make a referee of some paper, and a friend of mine, a very good theoretical physicist, has written an enthusiastic report, a very good paper. And then Kasia Grabowska, whom you know, has checked, and of course it is very good, with only exception that it is an error of sign at a certain point, which totally ruins the conclusions. Therefore, but Kasia has written that these problems of sign is a common problem of us, the theoreticians. Of course, so I try to avoid this problem. So again, it can be this vector, because the derivative is a vector, may be expressed in a new basis, yeah? Namely d over du plus d over dv. Sorry? Yeah. But at each point, it is a vector, yeah. Okay, yeah, you are right. You are right. But at each point, it is a vector. Therefore, and the coefficients are du over dx, and here dv over dx, and both coefficients are +1. Therefore, this is d over du plus d over dv. And finally, this operator, the wave operator, is nothing but, let me call this operator following Einstein. Of course, it is stupid because Einstein used it because it is a four-dimensional Laplacian. This is not four-dimensional, but two-dimensional. But excuse me.
And square is also two-dimensional.
Yeah. Okay, so this two-dimensional D'Alembertian is nothing by d over du plus d over dv square minus d over du minus d over dv square. And this is a nice exercise in elementary school, that squares will cancel, and what remains is twice the product. So altogether we'll have 4 times second derivatives of du dv. Okay. And now this enables us to rewrite this field equation in a very nice geometric way. Namely, whenever I have a rectangle in these variables, what is a rectangle? Rectangle is just something like that, yeah? Okay. So this means that, let me go back to my, so here, this line is u equal some quantity, say 1, and this u equal b, whereas constant line of the variable v are there. So let me call this line v, no, this one, v equal Oh, no. V equals C, V equals D. Yeah. So, and let us call this rectangle O. So the integral of this rectangle, if I calculate from, I will just, from A to B du, from C to D dV, this quantity, so rectangle of
U equals 0 instead of U equals A.
this is A.
No, downstairs on the picture.
Sorry. Excuse me. Yeah. Thank you very much. Yeah. Of this, which is 0. So what happens if the function fulfills this the wave equation? So instead of that, I put 4, I drop 4 because 4, so it is second derivatives of phi with respect to d du dv. So this is nothing but a b du, and here I have first derivative because we obtain at the point u and v is d minus d phi of u c du. Now again you integrate, so you finally get the value of phi at 4 points. Let me call these points A, these 4 corners, B, C, and D. So it is obvious that you will obtain phi at A plus phi of the opposite. What is opposite? C minus phi of B minus phi of D. Okay, now every solution of wave equation fulfills this, but the opposite is also true. It is very easy. I drop the proof. Everybody of you may easily prove it, that whenever you have a function on a plane which fulfills this equation, this identity, for any rectangle in variables u and v, then this function fulfills wave equation. Okay, so now, let me apply this. Sorry?
Does it hold in 5 dimensions?
No. In 4 dimensions, it is slightly different, but I will comment on that. Let me finish this example. No, it is not such a simple, but okay, so suppose we want to apply this philosophy. I will call it Brachistochron philosophy. So try to apply this brachistochrone philosophy to this problem. But you see, so first step in this brachistochrone philosophy is to impose boundary conditions. And later on, you derive field equations. So suppose you first impose boundary conditions. So now you check, does this boundary condition fulfills this identity? If no, there is no solution. Moreover, this set of, if you wish, the space of those boundary conditions which admit solution is very small. Oh, here it is very easy. In this particular example, it is very easy because you know that if you have imposed boundary condition on 3 walls, then this is already given. But if you choose, for instance, something where this is niewspółmierny I jakieś się... where this wall is incommensurable with that, then you see that it never closes, but you will have something like infinite identity, which is difficult, very difficult to analyze. But the situation is still not as bad. But if you take at random the volume U, then the situation is really very, very bad, because the set of all boundary conditions which admit any solution is very small. Mathematicians have is of first category with respect to the second category. In poor words, it is, I would summarize the situation in the following. If you just put the boundary data at random, then the probability that there exists any solution is 0, precisely 0. Therefore, my conclusion would be, you may accept it or reject, whatever you wish. However, my personal conclusion is the following. No. Okay. Oh. My personal conclusion is the following, and this is very standard situation, even if you take our old oscillator. So it is obvious when you take an interval of time, which is a multiple of period, then you cannot freely assume boundary conditions, because the position here must be equal to that, and also the momentum, and so on and so on. It is a very nice example. However, in mechanics, we may say, but it is a relatively seldom situation. But in field theory, it is not seldom. It is just the standard. Standard situation is that if you wish to reject this and next derive field equations from that time, first you must know field equations, because otherwise you get nothing. There are no solutions. Therefore, the procedure of deriving field equations, where we first must know already those field equations, is a nonsense. my conclusion is the following. Instead of neglecting this and concentrating on that, so I come back to my fundamental formula, which I am analyzing here is this formula. The derivative of the Lagrangian decomposed into two components, into two terms, the volume term and the boundary term. So the procedure, which I would call Brachistochrone procedure, which works perfectly for elliptic problems, and all those engineers, traffic engineers who are constructing green waves in Warsaw may legitimately use this procedure. For us, the physicists who are trying to describe fundamental laws of nature, is absolutely useless. Okay, and does it mean that Euler-Lagrange equations are false and we have to throw away books? No. Euler-Lagrange equations are correct, but there must be derived in a completely different way. Instead of neglecting that, whenever I neglect, this is an identity. There is no information here. This is an identity. Where I neglect this becomes an equation. And this equation, but I will keep that and neglect that part, which in poor words means that I am working on shell. I am not interested in those jets of fields, in those field configurations which do not fulfill field equations. No, I am interested only in those who fulfill. Therefore, for me, this is equal zero a priori. And now this becomes an equation. So let me now try to analyze what happens in such an approach. So this is paradox. I will never use that. So field equations. So whenever I have a Lagrangian, again, which depends upon fields and their derivatives. So there is a notion of a momentum canonically conjugate. And these objects, which I have used here as merely an abbreviation for something, I will call them P, K, mu. What are those? From the point of view of the values, of field values, they are just covectors. But they have an extra index, and in mathematical terms, but I'm not going to go very deeply into that mathematics, they are covectors on each fiber of this bundle, but not with values in scalars, but in vector densities on space-time. Everybody who wants to deepen his geometrical understanding may easily find all the explanations in papers, books, and so on. And the field equations are written in this way. So this is a standard way to write down field equations, which is because this derivative.
On the left-hand side.
Oh, sorry, excuse me. Yeah, sorry, excuse me. Which is nothing. By the way, at this point, I would probably just put D. Now, what is the difference between D and delta? I have published some papers, and sometimes I prefer to use d, sometimes delta. But at this very point, it is nothing but just derivative. However, we stand at a single chosen point of space-time. The independent variables are field strength and its derivatives. And this is just the standard derivative. And now, of course, this acts either on the first side, so d mu p k mu d phi k, or it acts on the second part, plus p k mu d, and of course, d mu enters here, phi mu phi k mu. So the function is a function on a first jet of section of this primary but on the other hand, we have those momenta and their derivatives. So you can say that finally here we have first jet of the section of this fiber bundle where our field configurations are described. And you may say that, and this is nothing but the first jet of those momenta, but not exactly. Why? Because the first jet contains all possible derivatives, and here we have only some combination, so a little bit less. So it is some generalized jet, some equivalence relations between all the jets is fulfilled. But in any case, you see that it is just nothing but a control theory. You have control parameters, the generating function, and you have the response parameters. And this equation means nothing but, first of all, the derivative of this Lagrangian to this parameter is equal to, so this equation is pk mu equal dl over d phi k mu, whereas the derivative with respect to this parameter is written here. Therefore, d mu p k mu is equal dl over d phi k. But please observe that when you plug this equation into Z, so you obtain simply Euler-Lagrange equation. Therefore, Euler-Lagrange equations are still valid this way. However, we have something more. Namely, we have first order equations for a bigger set of. Sometimes we prefer to have second order derivatives for calculational reasons. However, I believe that physically it is very, very nice to have this description, because in most cases which we deal in physics, this quantity is a very important ingredient of the geometrical description of the physical field which we deal with. So I prefer this version. Therefore, I may say the following, that the Euler-Lagrange equations can be derived from this symplectic generating formula. By the way, in physics, you have a lot of such generating formulae. For instance, I remind you, in classical thermodynamics, you have the generating formula, which is minus P dV plus T ds. Yeah, and you treat the internal internal energy as a function of control parameters, namely the volume and the entropy. And this equation means nothing, but if I know the generating function, namely how the internal energy depends upon the volume and the entropy, I know already everything. The entire physics of this body is already known, namely minus P is the derivative of U with respect to V, and T is and so on and so on. However, these techniques enables a lot of, I prepared much more examples, but I see that my time comes to the end, so I will skip more examples. Of course, okay, I will skip more examples. In any case, these techniques is very, very useful for the purposes, for the fundamental purposes, because we may exchange the role of control and response. For instance, you know that if you write this as minus dPV plus VdP, and then you put this on the other side, then you obtain the free energy, which is also an extremely important generating function in different circumstances. Yeah, when you discuss adiabatic processes, it is very useful to use that. But if you discuss if you put your body into thermal bath, it is much better to consider the other thing.
Yeah, not this is for enthalpy and for.
No, excuse me. Yes, of course, it's good. This is enthalpy. Yeah, the free energy, excuse me. The free energy is if I exchange T with that. Excuse me, because I am a little bit excited because my time is coming to the end, so I must somehow go to the end, and I will. And for example, general relativity is a beautiful example of the superiority of this approach over the standard approach. Why? Because in general relativity, we do not have only one geometrical quantity which characterizes space-time geometry, namely metric. Of course, metric is a legitimate quantity, very important, but we have also another one, namely the connection. And in the present version of general relativity, we assume a priori a certain relation between the metric and the connection. But of course, this is one of the equations. This is, I would say, this equation. We assume a priori this equation because the metric and the connection are mutually complement. Yeah, and of course, it is a legitimate problem to use metric and its derivatives as control parameters, and then we will have connection as the response. We may do it in such a way that this is just a standard. But I don't believe this is a fundamental law of nature. Of course, in our galaxy, let me say, we observe that probably, indeed, the connection is the metric one. But general relativity was invented as an extension of the Newton's gravity law from the scale of the Earth and slightly more to the scale of our solar system, and it works perfectly. However, to extend its present version, to the scale of the universe is still another extension by 20 orders of magnitude, roughly speaking, and it never happened in history of humanity that such an extension is possible. Therefore, I treat present cosmology as, of course, it is a legitimate thing to extend the theory and try to find the consequences, but it is just a mathematical exercise. Legal, but don't expect that this has anything to do with real physics. So I end up with this with advertising my approach, that there is much more room in this approach, and it does not lead to those absolutely crazy situation. Then in order to derive field equations, we have to know it before, which is which is a paradox which I do not accept. So I drop out a lot of things. The next part of my talk had been the so-called, but I will not go into details, but let me just tell you an advertisement for the next part, which will be dropped out. So the next part, I would like to discuss the Netter theorem, which very often is considered as a basis to understand general relativity, because it provides the right-hand side for Einstein equations and so on. In my opinion, Netter's theorem is absolutely useless in general relativity, because I have only two cases where Netter's theorem gives a correct energy momentum tensor. One example is a scalar field, and the second example is a continuous media. However, in order to have that, you have to be clever. You have to be clever. But already in electromagnetism, Netter's theorem gives you energy momentum tensor, which is neither symmetric nor equal to the energy, because we know what is energy of the electromagnetic field, and there is no doubt about that. So I wanted to discuss that, but I will skip. And at the very end, my plan, but I see now that it was completely stupid to have this plan, because I would extend this talk on 2.5 hours probably, so I will skip, but only let me tell you that the last part would be the discussion, how does it work in electrodynamics? Because in electrodynamics, when you there are apparently problems with constraints and so on, but observe that on the level before you integrate something, because people always say, let us pass to the Hamiltonian picture. In the Hamiltonian picture, we exchange time derivatives with the corresponding momenta, and we kill the boundary part, but now not four-dimensional boundary, but three-dimensional boundary, by imposing boundary conditions. This is legal. Imposing four-dimensional boundary condition is illegal, but imposing three-dimensional boundary condition, it is not only legal but necessary to make the evolution unique, or in physical terms, to make the field which is inside this three-dimensional volume and a closed Hamiltonian system. Okay, so then you have those constraints that the divergence of the electric field must be zero. And then there are those problems, those Lagrange coefficients, which is so complicated. Recently, I had a discuss with a very good theoretical physicist, a colleague of ours, who was shocked that those constraints arise when you integrate something over three-dimensional volume. So you derive this Hamiltonian density and you integrate over three-dimensional volume. You say, this is nothing but the energy contained in V. Very good. However, then you deal with infinite dimensional phase space. My advice is rather not integrate, rather try to analyze the story point by point. Of course, it is legitimate to integrate and to consider infinite dimensional system, but then it is much, much more difficult because you deal with infinite dimensional spaces, and the evolution operator, which is not which is an unbounded operator. Those unbounded operators Banach has invented Banach space in order to deal with partial differential equations. And we are teaching students in the second years how nice it is that all the theorems from finite dimensional space apply also in infinite. But it is cheating because it works only when this operator is bounded or continuous. But in in real physics, those operators are mainly Laplacians, and there is not a bounded operator. There is a lot of work to do in order to give appropriate self-adjoint extension to that, and this is difficult. Of course, it can be done, but when discussing physical properties, but it is not simple, which means that if you want to analyze the real infinite dimensional dynamics of the field, you must be aware of the fact that there is a lot of hard functional analytical problems. But most of the consequences may be derived on this level, finite dimensional level. Okay, thank you very much. Excuse me for extending a little.
Hello, Wojtek.
Yeah, thank you for the talk. Perhaps we have time for a couple of questions. So perhaps we start with the people who are online. Are there any questions from you?
This is Jacek Tafel speaking. This is not a question, but only I would like to apologize that I am not there. So I'm sorry that I didn't come, but I was not able because of some.
We are sorry that you are not with us.
Yeah.
Perhaps next time. Okay.
I have a remark which is on the blackboard. So
Yeah.
mainly because you said, okay, take this Lagrangian, take this fiber over a space-time point,
Yeah.
then we have a certain structure. But you know, those equations are interpreted as a Lagrangian submanifold, which
Yes.
is a certain
Yeah.
symplectic structure, which is given explicitly in those coordinates. But the thermodynamics, it's a different story. You have no symplectic structure, you have contact structure, which is different. So you cannot put all that this is sigma. This is different story.
No.
But of course,
You have-
the contact structure may be also interpreted as
Of
as
course.
a symplectic structure in higher dimension.
Yeah.
But on this level, it's a contact.
No. But I understand the symplectic space is four-dimensional, and I treat this of. I understand.
Space of thermodynamic variables. You cannot say that this is four.
It can be. Yeah, I agree. It can be formulated this way, but it can also be formulated in the way I like it, namely four-dimensional space, and this is the. Yeah. This contact formulation is useful, I agree, for certain purposes. It is useful. But for my purposes, it is useless. Okay.
No, because you have not only potential thermodynamics which come from these, but you can divide by all.
Yes.
Yes,
I agree.
Potentials, etc. And all this geometry is the same. It's a contact structure.
Okay, I agree.
Are there any more questions?
I would have a question. So suppose that we have higher order system, not Lagrangian, not of the second order, of the first order, but of higher order. So is this theory also applied there, or there's some
Yes,
difference?
it works perfectly. My answer is the following. I have written a couple of papers. There is one paper where everything is written. Yeah, roughly speaking, the poor man explanation is the following. If you have here derivatives up to 10, for instance, then you, as a configuration bundle, you take a space of 9th jets of the section. So the 10th derivative is just the first derivative of all derivatives up to 9. So this is, but then there are some technical problems because there will be some constraint in this, but it is easy to solve. Everything is well explained in my paper.
Okay.
Thank you.
I think we should stop because it's technically delayed.
Let me add just one more sentence. And what I didn't tell you is how we pass from the Lagrangian to Hamiltonian picture. And I believe that the Hamiltonian, the correct Hamiltonian formulation of a theory which contains more derivatives in the Lagrangian is relatively less known, but it works perfectly. Thank you.
Okay, thank you very much.